Okay, good morning, everybody, or good afternoon, or good evening, depending on where you are. Let's go ahead and get started. Welcome back to the second week of May Institute on Computation and Statistics for Mass Spectrometry and Proteomics. I hope that the first week was useful, and I also hope that this week will give us yet another view on especially statistical methods related to mass spectrometry and proteomics. But before we go there, so today we spend one more day on R, and today our focus is on working with R after we have already some experience with just reading the data, writing some simple scripts, and so on, so that we can actually start getting closer to not just doing some analysis, but doing analysis in a manner that is reproducible and reusable and usable for more than one project. Before we start, let me review some logistics in case you are joining us today for the first time. So at the bottom of your screen, you have a chat button. Let us use the chat only for things such as, hi, how are you? Or I can't hear, or something like that. And otherwise, for anything related to the topics that we discuss, there is a Q&A button at the bottom of your screen. Please use the Q&A for anything related to the presentation. This is helpful because then the instructor and the teaching assistants can answer the questions more effectively. And also at the end of the day, we can actually save the Q&A, and I will post a link to the Q&A to the docs document so that you can review the questions later on as well. And we hope that even though it's a webinar, it will be as interactive as possible. At the end, if you have any particular questions to the instructors or to the TAs, please stay back and we will be happy to answer questions more interactively. We can promote you to panelists so that we can have a face-to-face discussion. Okay, so now let me welcome our instructor today, Dr. Kylie Bemis. So Kylie holds a PhD in statistics from Purdue University, and Kylie's research already at the time of the PhD focused very heavily on R and on developing tools which are based on R. After her PhD, Kylie joined Northeastern University as a future faculty fellow, and currently Kylie is assistant teaching professor in the Curry College of Computer Sciences in the program of data science. And Kylie's work focuses a lot on teaching R and R-based programming for data science, but also Kylie continues to be a very active developer of software tools for mass spectrometry. In particular, Kylie is the lead author of the software Cardinal, which is a leading open source software tool for mass spectrometry imaging. So Kylie has extensive experience, and I hope that you will get to learn from her. And if you have questions related to Cardinal in particular, please don't hesitate to ask at the end. And I forgot to mention that Kylie holds a John Chambers Statistical Software Award from the American Statistical Association, which is specifically dedicated for excellent open source software. So we're very, very excited to have Kylie today as the instructor. And let me also welcome our teaching assistants today, Sai Laximetu and Sarah Tahiri. They are PhD students in the Curry College of Computer Sciences, and they both use R extensively for their research on a daily basis, so they're extremely knowledgeable, and we hope that they will be able to answer all the questions. Okay, so without further ado, let us welcome Kylie, and thank you very much, Kylie, for being here today.
Hello, everyone. Thank you, Olga, for the introduction. Let's see. Okay. All right. So Olga, I guess, already mentioned most of the things about me. So my background is in statistics. I develop a lot of R-based tools, and today we'll be kind of going through a lot of slightly intermediate advanced R materials. The idea is we're going in assuming that you have used R before, that you have kind of developed some of your own, or at least written some of your own scripts for analyzing data. You've used various R packages before for analyzing data, maybe some of ours, whether MS Stats or Cardinal or say MSN Base or something like that. But you don't necessarily have all of the advanced skills to, say, develop a package or to perhaps even write functions and things like that. So we have a lot of material to kind of get through. So we're just going to go ahead and try to see how much we can get through here. So let me go ahead and switch over here. So before we dive into the actual kind of coding and programming with R, there's just a few things I want to go over first. So an important aspect of a lot of what we do, both in our lab and as programmers and R developers and statisticians or data scientists, is making sure that our research is reproducible. So this is especially important when we're doing novel research, when we're analyzing biological data, and want to make sure that if we reran the same, if we reran our analyses, that we're going to get the same results. If we send our data to someone else, they're able to reproduce our results, so that we know that the work that we're doing is trustworthy and reproducible in that way. So I just want to quickly touch on some of the tools that we have for making sure that our work is reproducible, and some of these tools are also important when it comes to collaboration and developing R packages and working with R developers. So I just want to get a quick sense of how familiar some of you are with some of these topics. So we're going to start off by talking a little bit about R Markdown. Probably most of you have at least heard and maybe used R Markdown, but this is something that we use to write our vignettes so that our analyses are reproducible. And then we'll also talk a little bit about Git and Github, which are version control software. So I'm just going to launch a quick poll, see how familiar some of you are with these topics. And this will just help me get an idea of how much time to devote to the different topics we'll be going over.
Kelly, could you clarify, this is for all three or just for the R Markdown?
All three. I imagine most people have at least seen or heard of R Markdown, but either way, it's the kind of the easiest of these three. So focusing more on the Git and GitHub part. All right, looks like we have a good mix of inexperience and some experience. So I'll go ahead to make sure that we touch a little bit on these topics to get you an idea of what they're about. So first up, we have R Markdown. So R Markdown is a tool for turning our analyses into reproducible reports. The idea behind this is that if we're just writing an analysis script, that's going to be fine, but it's not necessarily going to be presentable to a wider audience. So we want a way to generate a report on what we did that also encompasses the actual code that we ran along with the results from running that code for doing our analyses. And so the goals here are to turn statistical analyses into some kind of publishable reports, and to make sure that our analyses themselves are reproducible. So quick question on the version of R. So I wouldn't worry too much about the version of R as long as you have 4 or greater. So I'll be making some. Later in the session, I'll talk about a few things that are new in R 4.0, but there's not a lot that highly depends on whether you have 4.0, 4.1, or 4.2. So you don't need to worry too much about the specific R version as long as it's 4 or greater. And even if you have something older than that, most of this will be applicable to most R versions, but I'll try to mention when we talk about some things that are more relevant to more recent versions of R. So back to R Markdown. So we want to turn statistical analyses into reports. And if you've ever used an R package, for example, from CRAN or Bioconductor, especially from Bioconductor, most of those packages have what we call vignettes. And so these are kind of reports or tutorials that show off what kind of analyses are possible and to kind of show you how to perform analysis. So just to show you a quick example, so I'm going to go switch over to my browser here. So this is one of my packages, Cardinal, which is a tool for mass spectrometry imaging. So this is the page on Bioconductor. And if I scroll down here to documentation, here's an example of a vignette. So this vignette was written in R Markdown, and it's just a tutorial showing how we can run different kinds of code, showing you how to use the package, and it combines both the written document as well as the actual code and results from running different parts of the analysis. So this is the goal of R Markdown. So it has two components: actual R code. So we have chunks of R code that will make up our analyses, and then we have a language called Markdown. So Markdown is what we call a markup language. So that means it's kind of like a programming language, but it's just a set of simple formatting that allows us to format what the text will look like. So what you're probably used to writing a document in, say, Microsoft Word, and Microsoft Word is a what you see is what you get editor. That means you can kind of change the font through a drop-down menu, and then you see the font changed in the document itself. So Markdown is a markup language, which means we're going to be using kind of some programming to change the formatting of our document. So the idea again here is to turn R code into high quality reports. And whenever we change the R code, or if we want to change the input, maybe use a different data set, we can then recompile that report and have new updated results. So the report is kind of a living document so that we can rerun it whenever there's a change in R versions, a change in packages, a change in the data, or anything like this. And we can see what the new results look like then. So in RStudio, it's relatively easy to create an R Markdown document. So I'll just show you in the slides, and then I'll jump over to RStudio and show you how to do this. So we would go to the plus menu to create a new source file, choose the R Markdown format. R Markdown can be output to different kinds of formats, including HTML, PDF, even Microsoft Word. And then once we've created the R Markdown document, RStudio will create a kind of skeleton template that we can add our own code to, add our own markup to. And then from there we can, it's called knitting, to compile into a finished document. So let me go over to RStudio. So you can see that the different example code that we'll be working through today, these are in R Markdown documents already. So we'll be working with R Markdown documents throughout today. So I'm just going to go to the plus button here to create a new R Markdown document. Call it example. Saying this is my author date, and I'll say the output is going to be PDF. And so you see, as RStudio creates a kind of skeleton template for me. So we have some information here at the top, title, author, the output format, and then we can write our code chunks in these areas. So to create an R code chunk, we just use 3 backticks. So these are not apostrophes, not quotes, but backticks. So on a US keyboard, it's the same it's the same key with the tilde or squiggle mark, so it's a backtick. And so we use these, and then we have curly braces, and then the letter R to indicate this is an R code chunk. And then we can just have R code inside of these. And then what you see outside of the code chunks is just text. And you can see some of the markdown formatting. So this, the 2 pound signs here indicate that we're using a header or a title. So our markdown is the header of this section. We can use emphasis by just surrounding words or sentences in either asterisks or underscores. And we can, in our R code chunks, we can also have plot output. So here I'm just going to click the knit button in RStudio to turn this into a PDF document. First I'll need to save it real quick. I'm just going to save it on my desktop. And so it's going to compile. And then let's see, so here is the output from that. So we went from the R Markdown document, which has a mix of Markdown formatting and R chunk code, to this R Markdown document. So this is how we would prepare a report. You can use all different kinds of Markdown formatting to make it pretty and polished and presentable. And then there's also a bunch of different options to format the code chunks, whether we want plots displayed, how we want those plots displayed, and other things like this. So that's the idea behind R Markdown. And as I said, there's a lot of different ways that you can format using this Markdown markup language. So here's just a few examples for different ways to format your text, get different headers, create lists, bullet points, and so on. We can use, and the R code chunks are run just in order, exactly as we've written them. And so all of the plots, all of the results in that report are generated directly from that code, and we can see what code was used to create that. So there's a lot more that you can do with R Markdown, but this is just a quick introduction to kind of get you familiar with R Markdown so that you know what kind of documents that we're looking at when I'm walking through the example code. So you know how we create things like vignettes when you see them in R packages. And just so you have an idea that this tool exists to create reproducible, polished reports using R code. Let's see. There's a. All right, so let's go ahead and move on to Git and Github. I don't see any open questions right now. So let's talk a little bit about Git and GitHub. So another aspect of reproducibility is making sure that we can actually manage our code for our analysis scripts so that we know we're always using the correct version, we're always using the most up-to-date version, and so that when we collaborate with other programmers, other developers, or other researchers, that we all know that we're working on the most up-to-date version. And so think for a moment how you would usually kind of manage files in a project. So you might think of a workflow that looks kind of like this, where we have where we write a version of our document or a version of our code, and then we just keep creating new versions. And if we're not sure which version of the analysis is the correct or better one for our, or more appropriate one for our data, then we might just save two different versions. We're not sure which is which. We might not be sure which is the most up-to-date version, and so on. And so there's we have tools called version control software that exists to kind of solve these problems, especially within the realm of programming. So the idea behind version control is give us a way to manage complex projects where we have many, many files. We'd like to be able to track the changes that we make, see what all of the different versions are, be able to go back to earlier versions if we want to, know who made different changes so that there's a record of all of the changes that we've made, and also to be able to easily share with our collaborators. And so we want to be able to track changes made to a project, even if it's across multiple files. When we're working on a complex research project, it's often the case that we don't just have a single analysis script or a single version of our paper. We might have many of these. And so we want to be able to track changes not just within a single file, but across multiple files. And especially if we're working on software that other people might use, such as if we're developing an R package, then we might want to be able to track multiple branches of progress. So this is something that often comes up as an R developer when we have an R package that people are using, and we want to make a new feature, but we don't want to disrupt the stable working version that people rely on. So we want to be able to make different branches, merge them when we need to, and also synchronize work with our collaborators. And so this is the goal of version control software. So there's a little bit of vocabulary to be aware of when we talk about version control systems. So when we talk about a version control software, we often talk about a repository or a repo. And so a repo is just something that stores all of the files in a project that are tracked together. And then if we want to kind of save a snapshot of our repository and all of the files in it at a certain point in time, we make what's called a commit. And a commit is essentially just that. It's just a snapshot of a set of changes that we make at a certain point in time. The project head is what we refer to, or what we say to refer to the most recent commit. So we're working on a project in a repository. We make changes. We make a commit, which is a snapshot of the current changes. And wherever we're working at the current point, the most recent commit, that's the head of the project. And then we can push and pull changes from one repository to another. So we have a version of our repository, our collaborators have their own versions of the repository, and we want to be able to push and pull the changes between them to keep everyone in sync. Another thing that we want to be able to do is to be able to look back in the history of the repository and see what changes have been made. So we have, whenever we make changes, those changes depend on what changes we made before. And as we said, we want to be able to track it when we have different branches of development, so that if one of us is working on a new feature, that's separate from the main branch, or what we would call the trunk, which is the more stable version that people might rely on. And so some of the most popular tools for performing this kind of version control, we have two tools I'll talk about. So the first is Git. So Git is an actual version control software. It's what we call a distributed version control system, because every person working has their own copy of the repository. So I have a copy of our entire repository. My collaborators each have their own copy of the entire repository, and each repository is a fully fledged version control system on its own. So we each have a copy of the entire history of our repository. And what this means is there's no need to rely on a central server. We can always just take our machine wherever we want, even if we don't have internet access, make changes, make commits to our local repository, and then when we have internet access again, sync those changes with our collaborators. So we don't have to rely on any central server to track these changes, which is something that older version control systems used to need to do. So that's Git. And then there's also GitHub. So I want to make it clear that Git and GitHub are two separate things. So Git is the actual version control software that we can use on our own computer, that our collaborators can use on their computer. And then GitHub is a website that hosts online Git repositories for free if they're open source and public. And so GitHub is a tool that we can use to share our work with collaborators, with the public, and for all kinds of collaboration and open source sharing. So I'm not going to walk through the steps of installing Git or making sure that Git is installed. So this is something you can come back to and check later. But when you're first setting up Git, you need to make sure that it knows who you are, so that it has your user name, your email, so it knows who is making changes. And then it's really easy to set up a Git repository. I'm going to show you kind of the command line version. There are GUI, graphical user interface, applications that you can use with Git and GitHub. So there's a GitHub desktop that you can use if you're more comfortable with a graphical user interface. But there's different versions of those. They have different capabilities. The command line version is always there and it's always the same. So that's what I'm going to show you. So you can always just start a new Git repository by navigating to a directory in your terminal and typing Git in it. But I'm going to show you another way to start a Git repository on GitHub and then start working on it locally. So here I'm going to go to GitHub. So if you do this, this requires a GitHub account, which is something it's a good idea to have, because it means even if you don't end up using GitHub for your own repositories, it allows you to say open issues on R packages that you might be using if they're hosted on GitHub, and things like this. So I'm going to go over to new here. There's a couple different places, so I can go up to here, new repository, or I can do it over here. And I'm just going to call this example. And then I'm going to add a README. So you can, if you know you're working on in a particular language like R, you can tell GitHub that, and it'll create what's called a .gitignore file. And so there's lots of things that we don't necessarily want to end up in a Git repository. So code, text files, these things are all things that we want to store in a Git repository, but we don't necessarily want something like large binary files or temporary files, things like this being tracked. And so that's what goes into the gitignore, is a list of files or file patterns that you don't want tracked. All right, so I'm just going to go ahead and click create. And then what I'm going to do is I'm going to go over to code here, and I'm going to copy this link. And so you should see my terminal window now. And so currently I'm in my May Institute 2022 folder or directory, and I'm going to go ahead and clone the repository I just created on GitHub here. So now you can see that a new directory has been created. So this example directory didn't exist a moment ago. If I go into that example directory, you can see, well, currently the only thing exists is this README file. So that's all that's there right now. But I can create new files if I want and track changes. So I don't want to spend too much more time talking about Git and GitHub, since I know the main goal of this session is to talk about R and R programming. So I'm just going to kind of quickly skim through the rest of this. You can come back to these slides as a resource later, or look at one of the linked tutorials or something like that if you want to kind of know a little bit more about Git and how to use Git. But I just wanted to at least introduce you to Git and GitHub because they are important technologies that are used by a lot of programmers, by R programmers. So if you're ever interested in, say, developing an R package and submitting it to Bioconductor, that's going to be done through GitHub. And so you need to have your package available on GitHub in order to submit it to Bioconductor, as an example. So there's a few main Git commands that are important to know. So git add kind of adds files to what we call the staging area, which is where files go before we create a commit. So a commit being that kind of snapshot of the current state of the repository. So we have this workflow of git add files that we've changed, git commit to create that kind of snapshot. And then we use the commands git push and git pull to synchronize changes between our local repository and a remote repository. So what a workflow typically looks like is we'll have our own local repository that we do our actual work on. There's a remote repository that lives on some, say, a GitHub server. And then our collaborators also have their own local repositories. And we push the changes from our local repository to that remote repository. And then when our collaborators want them, they can pull them down from that remote repository to theirs. And then we can get their changes by pulling them from the remote repository to our local repository. So that's just kind of a quick cheat sheet of some of the most important Git commands to get started. And so what a typical workflow will look like would be to make sure that you've gotten all of your teammates' changes from GitHub by using git pull. You would make changes to your local repository, so update files, make changes to your code, whatever new edits that you're working on. You would stage those changes for a commit by using git add. You would commit them with git commit, and then you would push your changes to GitHub with git push. So that's just what kind of a typical workflow looks like. So I don't want to spend too much more time on this, as I said, since we do have a lot of R programming material that I want to get to, and I know everyone is probably more interested in. So I'm just going to go ahead and leave things there unless there's any pertinent questions that you'd like me to quickly cover here. And if so, go ahead and ask them in the Q&A. All right, so I don't see any open questions on this topic, so we'll go ahead and move on. So again, just all right, there we go. So all of the course materials for this session are on GitHub, so you can just download the files individually. You can download the whole repository if you'd like, or just look at them online. However you'd like to do this, I would suggest just downloading the whole repository as a zip file and then going through the R Markdown documents as we work through the code together. And I put that link in chat if you don't already have it from the May Institute document. Okay, so let's go ahead and talk a little bit about functions and functional programming in R. So the goals for this topic, I just want to review some basics of R so that to make sure we're all on the same page. We'll talk about writing functions, and then we'll talk about functional programming with R. So just to review some R basics, some of which you might not know, some of which you hopefully already know. So a brief history of R is that there was a language called S created by John Chambers and a team at Bell Labs back in 1976. The idea behind the S language was to turn ideas into software quickly and faithfully. So the issue at the time was computers were still rather difficult to program. Fortran was kind of the predominant language for doing any kind of data analysis. And Fortran was not very easy to program with. I would say it still isn't very easy to program in Fortran. And so the original idea behind S was to essentially create a language that allows statisticians and data scientists to quickly create analysis scripts that can call some of the Fortran subroutines that people were relying on for data analysis and statistical analysis. Over time, S became a whole language of its own. People started writing analyses in S rather than just in Fortran or C later. And then at some point, Robert Gentleman and Ra Sahaka created the R language, which is a free and open source implementation of S. So they created that in 1993. And so it's the goal there was to kind of implement most of what existed in S at the time, but in a version that's free and open source, because S was a proprietary language, so you had to have a license in order to use it. There's a quick question on Git. So question, can we move between commits? Yes, so there's different some different Git commands that you can use to change what to revert to an earlier commit. So I think Git revert is one of the ones that you would use to revert to an earlier commit. But yes, that's one of the goals of version control software, is to be able to go back to earlier versions if you need. And then something that we mentioned, but I didn't show you as much, is also having different branches, so different versions of the same repository. And so if you're working on different versions, you can also use git checkout to switch between different branches of the same repository. So R, free and open source implementation of S. It's influenced obviously by S, but also by a language called Scheme, which is a dialect of the Lisp language, and xLispstat, try saying that 3 times fast, which is another dialect of the Lisp language, specifically for statistical analysis. And so that one was developed by Luke Tierney, I believe, who is still a contributor to many of the improvements in R. And so that brings us to the modern R language. So we have it's a powerful environment and language for statistical computing. We have interfaces with C, Fortran, and a number of R languages, a number of other languages, but a lot of analyses these days are even written in pure R. But we can access other more performant languages like C and Fortran if we need to perform heavy lifting and very fast numeric computation. So R is very flexible and extensible. There's over 10,000 user contributed packages, which is part of what makes it so powerful, is that if you look up any statistical paper with a new statistical method, there's probably an R package that accompanies it, written by the researcher who developed that method. So it's very up to date with a lot of the current methods, and you can get access to many different methods. I see a more of a comment than a question about using Fortran back in 1976 and programming with punch cards. That's my father did that as well. So my father is also a statistician, actually. And yes, we've come a long way since then. So some of the features, or some of the ways we would describe R as a programming language, is that it's interpreted. What that means is that we can evaluate R code line by line we don't have to compile the entire code base first. So in compiled languages like C or Fortran or C++, we have to run a compiler to compile the code that we have into an executable that we can run. With R, we don't have to do that, so we can run it interactively. R is a functional language. That means that functions are a first-class citizen in R, so we can pass functions around as regular objects. A lot of the emphasis on programming in R is based around using functions and applying functions to elements of a list, columns of a data frame, or things like this, rather than iteration using things like for loops. R has dynamic typing, so that means that types belong to the objects rather than variables. So variables, we don't have to be declared with a specific data type. Instead, a variable can be reassigned to any type of object whenever we want. This again leads to a lot of flexibility and makes it easier to type the code, but it can lead to some troubles because we don't always know exactly what kind of object we might be getting. So that has some potential for difficult to track down bugs. R is lexically scoped, so that's just means there's some specific rules around how R finds what value corresponds to the different variables. And lexical scoping, we'll talk a little bit more about that. And R is also an object-oriented programming language. So there's actually two different, or two dominant types of object-oriented programming available in R, S3 and S4. We can look briefly at both of those, but I'll probably focus on S4 later since Bioconductor primarily uses S4. R has several what we call atomic data types. So everything is a vector in R, so there's no scalar types. So these atomic data types in R are all vector types. And by atomic, that means that every element in the vector is of the same type. So character vectors are vectors of strings. Doubles and integers are types of numeric vectors. We have logical vectors for true, false, as well as missing. Those are the main types we'll encounter. There's also two types called raw for storing kind of just raw binary bytes, and complex for complex numbers. Question. I mentioned something about compiling when we were talking about, I believe it was actually R Markdown. We were talking about compiling in R Markdown. So the compilation I was referring to when it comes to compiling an R Markdown document is really just the process of running the code and outputting it into a static report document. So it's not really compiling the R code itself as so much as just running it. So rather than a code compiler, you can really think of it as just literally compiling together the different parts of a report and putting it into a final version of that report. That being said, R does actually have a byte compiler that I might talk about, but I don't know if I will. But for the most part, R is interpreted. Question on integer versus float. So we have two numeric types, well, really three if we count complex, but two main numeric types in double and integer in R. So the doubles are 64-bit floating point. The integers are 32-bit integers. So for better or worse, in R, we do not yet have access to a built-in 64-bit integer type. And the doubles that we have access to are all 64-bit floating point. Some of the non-atomic data types in R, we have lists, arrays, matrices, and so on. So non-atomic here essentially just means it has more complex attributes than just a vector where every element is the same. So when we talk about operating on things in R, well, as I said, everything is a vector. So there's really no such thing as a scalar type in R. So numbers, strings, they're all vectors of strings, vectors of numbers. We're always working on a vector. So that means all standard arithmetic operations are vectorized in efficient C code. We have a linear algebra powered by BLAS and LAPACK. And so whenever we want to work on things in R, we want to take advantage of what we call vectorized operations as much as possible. And we rely heavily on functional programming for a lot of things. All right, any quick questions on R basics before we talk about writing functions? So a quick question on atomic versus non-atomic data types. So just to reiterate, the atomic data types here, you can think of atomic as kind of like primitive. So these types cannot be broken into any smaller pieces. So these are the simplest types in R. They're for commonly representing data. They are vectors. Every element is of the same type, so we can't break these types down into any smaller building blocks. So we have character vectors as vectors of strings, doubles and integers as vectors of numbers, and so on, and there's no smaller pieces than that. Whereas the non-atomic types, like lists can contain different types of vectors. Arrays and matrices both have additional attributes that define the dimensions. They can have so we can have multiple dimensions that also have to be considered, and so on. So that's the difference between the atomic and non-atomic types. All right, so there's a nice quote from John Chambers, creator of S and still an important member of the R core team. So he says this: to understand computations in R, two slogans are helpful. Everything that exists is an object. Everything that happens is a function call. So let's take a quick look at both parts of that statement. So everything that exists is an object. So that means everything that we can possibly have in R exists somehow as an object. And what that means is that even R code itself can actually be represented as an object in R. And so this is something that's a very kind of a hidden feature that many people might not make use of, but it is heavily used in some very well-known R packages. So if you've ever used any of the tidyverse packages, whether that's ggplot2, dplyr, any of these, so these rely on the fact that everything in R is an object, including the code itself. We can represent R code and R expressions as objects that we can manipulate. And that allows for a lot of interesting non-standard evaluation. And that kind of comes to how packages like ggplot2 and dplyr are able to say, for example, allow you to reference the columns of a data frame as if they were variables. So I'm going to go back into RStudio for a moment. So here, let's take a couple quick pieces of simple R code. So here we have, we assign 2 to X, we assign 3 to Y, and then we evaluate X plus Y, and that's 5, right? So relatively simple. But what actually happens when we run really any of these lines? So what I'm going to do here is I'm going to actually capture X plus Y as an expression. So I'm going to use this quote function to capture that expression as a language object. And so here, if I look at the type of this variable that I just created, it's a language object. And I've called this sexp or S expression for reasons that will might not talk too much about, but essentially R and many Lisp languages are built on what's called S expressions. So that's why I'm calling it this. But anyway, so here we have a variable that is really just, it's a language object. And so if I call the eval function on it, well, it'll evaluate x plus y, and we'll get 3. Or excuse me, we'll get 5, because x is 2, y is 3. So if I evaluate that code, I'm going to get 5. But I can actually manipulate this object. So if I say access one of the elements of this object, say the addition sign, I can replace it with a multiplication sign. So I've modified the actual code here now. So I've changed it from x plus y to x times y. And then I can evaluate that as well. So 2 times 3 now is 6. And so the key point here is just that everything that exists in R, including potentially the code itself, can exist as an object that can be manipulated with code, including the code. And so that's a really cool thing about R that, again, is not necessarily something that you'll use as a regular R user, but is something that a lot of R packages take advantage of to make programming a little bit easier. And so again, this is something used heavily in tidyverse packages as an example. Let's take a look at the second part of that statement. So everything that happens is a function call. So that means essentially all operations in R, everything that quote unquote happens is a function. And that includes things that you might not necessarily expect to be functions in a programming language. So even things like assignment of variables is a function call. Parentheses even are a function call. So let's go back over to RStudio again. So here, let's reconsider that those 3 lines of code we were looking at before. And what those are really doing is the same as these 3 lines of code. So we can actually just rewrite what we did a moment ago using this familiar syntax, using this different syntax, which makes it explicit that what is actually happening is that we're calling functions. So the assignment operator is a function. And you can see I'm quoting it with backticks because that's a way that we can use non-standard variable names in R. So quick hint, if you ever need to look up documentation for something like the assignment operator, you can surround it with backticks. It's not going to work if you don't do that. But if you quote it with backticks like that, that tells R this is a name rather than actually trying to evaluate it as code. So saying this is a name, let's look it up as a name. Say a variable name, an object name, whatever. And so I can call this assignment operator like a function. Let me go ahead and remove x and y from my workspace. So there's no more x, no more y. But after running these, now we have x and y. And I can use the addition sign also like a function call. So really, we're just rewriting what we usually use is called the infix notation, where we can write the function name in between its arguments. That's what we typically do for arithmetic operations or for assignment and things like this. And we've written them using prefix notation, which is the way that we usually call functions. So everything in R, including the assignment operations, everything is a function. And in fact, I can, even the parentheses can be a function. So let's say, if you want to be really insidious, you can define parentheses or curly braces as a function in your friend's workspace, and that'll really mess them up. But no, in reality, don't do that, because that's going to be horrible. But you can do it, because even parentheses, even curly braces, all of these are function calls. You might see the return statement in an R function, not often, because we don't often use a explicit return statement. R functions just return the last evaluated value. But if you do use the return, that's still just a function. It's not a reserved keyword like it is in other languages. So this is really kind of what we mean when we say that R is a functional language. Functions are everywhere in R. Everything that happens is a function. Functions themselves are objects that we can manipulate. We can assign functions to variables. We can manipulate functions. And moreover, functions can capture what we call state in a way. So functions can capture their environment. That means when we define a function, that function is aware of the environment in which it was created. So it has access to any variables that existed in the same environment where it was created. And that's something that comes up when we talk about lexical scoping. So if I create a new function in my global environment, it's going to have access to any of the variables in my global environment. So the specific components of a function, there's 3 components of a function in R. So we have what are called the formals. So these are the parameters of the function. We have a body. That's the code that is actually evaluated when we call the function or execute the function. And then a function also has an environment. So this is where it finds the variables that it references. So if I go back quickly to RStudio here, I'm going to define a simple function called add. And so I wanted to use add, say 314. It's just going to return x plus y, which is 7 here. So remember, when we write an R function where we don't need a return statement, it's a function in R is just going to return the value of the last evaluated expression. So we can see the different components of the function. So the body of this function is just that code x plus y. The formals are those named parameters x and y. These could potentially have some kind of default values. So if I go and redefine this, say x equals 0, y equals 0, and then I take another look at the formals. So the formals will include the names of the parameters as well as any default values associated with them. And then the environment is a part of the function as well. So the function captures the environment where it was created. So in this case, the environment for this add function is the global environment, which is where we're typically working when we're just writing an interactive R script. And so if I can see what variables exist in that global environment. So we have the add function itself, that sex variable from earlier, as well as x and y. So these are the variables our function will have access to in addition to whatever formal parameters it has. So to define a function in R, it's quite simple. We just use the function keyword. We give it, we call it like a function. In parentheses, we have the names of whatever parameters we want that function to take. And then after that, we have the body of the function. Now that body can either just be a single line. It could be multiple lines like this. Anything works. We can have multiple lines like this. That works as well. And then we can assign that the result of that whole thing to a variable name. And then that variable name is then how we can call that function. So that's how we can define a function in R. So I want you to think for a moment now, and actually first let me get a quick poll on how many of you are already experienced with writing your own functions. All right, great. So it looks like we have a number of people who are not very experienced with writing functions. That's great. So we'll learn something already. All right. So think for a moment about why you might want to write your own function in the first place. Let's see. So why might we want to write a function? So there's a few reasons. The simplest reason is to avoid duplicating code when we don't need to. So we don't want to have to copy paste if it can be avoided. So if you've ever written an R script to do some kind of analysis and you find yourself kind of copy pasting chunks of code that you use a lot, that's probably a very good candidate to turn that into a function so that we don't copy paste that. And just to make clear, copy pasting is bad because it's an easy way to introduce errors or bugs. If we're copy pasting code, that means there's more things that can go wrong. There's more little things that we might have to change to make it appropriate for our current data set or the different columns in our current data set and things like this. So code is not very reproducible if we're copying pasting it. Writing a function is going to be much better. Having a function makes it easy to reuse a common workflow because we then don't have to copy paste it all over the place. And importantly, it also makes it easy to share that functionality with others. So rather than having someone else try to modify an R script that you sent them and try to figure out which parts they need to change to make it work for their data. Instead, you can put that functionality into a function and they can just pass their data into that function and get the analysis results much more easily than trying to change the different parts of the script to make it work. So here's an example. So suppose that we want to replace the missing values in all of the columns of a data frame with the median value. So we're going to impute missing values with the median of the non-missing values. Well, suppose we have a data frame with columns like age, time, year, rate, and so on. Well, one way that we might go about doing that imputation is the above code here. So we can use the if-else function. So if-else, if you're unfamiliar, if-else takes 3 arguments. It's a vectorized if-else. So the first argument is going to be it's going to evaluate to a logical vector. So isNA is the function that we're using here. So this is going to return a logical vector with trues where we have missing values and false where we don't have missing values. And then the next 2 arguments to if-else are going to be the elements that we use when the first element is true. So whenever this is true and it's missing, we're going to get replace it with the median. Whenever this is false, we're going to replace it with the existing value, the same value here. And so if we wanted to do this with each of these columns, well, we could just copy paste it like I've done here and change the column names. But as you might see, this isn't very reliable because then we have to change the column name each time. And if you're looking closely, you might have noticed I actually made a mistake even here when doing this. So I didn't remember to change the column names in every case here, which is something that can definitely happen if you're doing this at home. And so this is much less readable and much less reproducible than this version. So here we can take this expression and put that into a function that's going to be easier to use. So as an example, we'll go over here. So we're going to write a function that replaces all the missing values in a numeric vector with the median value. And so here is the version of this that I've written. So to write an R function, again, we use the function keyword, which is really just a function itself. We enclose in parentheses any of the parameters that that function is going to take. And then after that, we have the body, the code that is going to be evaluated whenever we call that function. And inside the body, we can use any of the parameters that that function takes. We could also use any variables that are in the same environment that we use to create the function. So here we're going to use the x that's passed. So here is an A. We're going to replace it with the median when it's missing, or just use the original value when it's not. So here I'm going to create that function. Here, let me create a simple sample. So here's an x, actually, let me call it y, just to show that the x here is not going to be the same x necessarily. So right now I have no x in my global environment. I have a y. Here's my input NA function. I'm going to use impute NA on y, and you can see that it gives me the following. So what was the median here? Let me see. So I think that was 3.5. Yeah. So the missing values here got replaced with 3.5. So suppose that we want to make a more flexible version of this function. So here in this version of impute NA, I have kind of hard-coded it in that the value we're going to use to replace missing values is going to be the median. But what if we wanted to allow the user to decide what that method's going to be? So that's something to consider when writing a function is how can we make our function more flexible to the needs of different kinds of users? So suppose someone wants to impute missing values with the mean rather than the median. So let's add another parameter that the user can change to decide whether we want to use the median or the mean to do the imputation. So here's another function that I'm writing. I'm going to call it impute NA2. And I'm going to have another parameter. I'm just going to call it method. And this, I'm going to assume that this is going to be a string specifying either median or mean. And so here I have a if else. And so first I'm going to say if the method parameter is passed as median, then we're going to go ahead and do the median version. Otherwise, if method is mean, we're going to use the mean function to do the imputation. So let me run that. So now this is my new function that I've just defined. And so let me go ahead and call it on this vector. And I'm going to say I want to impute with the median. Just to, let's quickly see what the median of this is. 5.5. So here I've replaced that missing value with the median. I can change this to mean, and it'll be replaced by the mean instead. Now, in this case, there's no real other option. So if I change it to say something like max, it's just not going to do anything because I only handled those two possibilities here. All right, so there's a few things that I can do. So we just did this exercise to implement the impute NA function. So some things to consider when writing a function and thinking about whether it's going to be a good function. So some of the things that we want out of a good function are that it's obviously correct. So when you're writing the code for a function, you want to make you want it to be kind of obviously correct in that that what the function is doing, the code in its body is clearly doing the correct thing. This is something where you can use code comments to kind of try to make it more clear, but a very good function should be relatively easy to read and obviously doing the correct thing. So some of that means making sure that you're using variable names that make sense. So don't just call everything temporary or X and Y necessarily. Instead, explicitly name different variables such as, say, mass or intensity and things like this. A good function should be specific and simple. So a good function does one relatively specific thing very well. So we just showed kind of making a function a little bit more flexible by allowing the user to specify how the missing values are imputed. But we don't want too much flexibility because then our function can get quite messy. A little flexibility is very good. Too much flexibility can make a function difficult to understand and especially maintain later. So too much complexity can introduce a lot of bugs is a general issue. A good function should be concise but readable. So if you probably don't want a 100-line function. A good function will be maybe a dozen lines at most, maybe a little bit more. But the kind of thing that you want to do when approaching functions is you want the code to be, again, relatively short, compact, obviously correct, and concise. If your function starts getting too long, then you might want to start thinking about how can I break up this big function into multiple smaller functions. So you can create smaller helper functions that do some of the work as the one bigger function. A good function should have an intuitive name, so it's clear what it's actually doing. So make sure that the function kind of does what it says. And then, of course, speed. So how fast is the function? But this is something that we'll talk about improving performance a little bit later in the session. But you don't really want to prematurely optimize your code until you know that it's too slow. So if you know that you can do something fast without sacrificing readability, then go ahead and do it. But you don't need to, it's not a good idea to spend too much time trying to figure out how to optimize a function unless you know that's actually going to be an issue. So let's look at just a couple more potential improvements that we can make to this function. So we talked about default arguments a few minutes ago. So that's another thing that we can add here. So we can see, for example, that if I try to call my previous function without specifying how we impute the missing values, well, it's going to tell me method is missing. And we'd like to be able to allow users to just call impute NA without having to specify whether it's median or mean or whatever. So this is a good place to introduce a default value for our parameter. So here we're just going to specify a default, so method equals median. So I'll run that now. And so now if I run that without any additional arguments, just going to use median to impute. But I can still change it to mean if I want to. A useful way of kind of explicitly specifying all of the possibilities that an option can have, because method, it can only really be median or mean in my function right now. So I don't want the user to try something else like I did earlier and not get a useful result, or at least a useful error message. So something that we can do is we can actually specify all of the allowed options here. So here I'm giving a character vector, giving the allowed options, which are median and mean. And then there is a neat little helper function called match.arg that I can use. And that will, first it'll check if the user provided an argument here, and it'll use whatever the user provided first while matching it to these options. And if the user didn't provide an argument, then it'll just match it to the first one. So in this way, the first value in this vector is still going to be the default value. And so I just add this additional line, method is match.arg on method before the rest of the code. So you can see now, so if I run this without specifying anything, I'm going to end up imputing with the median. But I can also impute with the mean. And part of what this match.arg function does is it'll also do partial matching, which you can argue whether or not that's a good thing or not. But I can, for example, put med, and that will get matched to median as well by match.arg. So let's take this even one step further. So rather than forcing the user into these two specific options, one last thing that we'll do here to make our function a little bit more flexible is actually allow the user to pass in a specific function. So here, let's just go ahead and allow the user to pass in a function. And this is something that we can do because R is a functional language. Functions are first-class citizens. They can be passed around like any object. And so here, I'm going to say that the second argument, the second parameter here is fun for function rather than method. And the default is going to be median. And median without quotes here, this is going to be the function, the actual median function. Just like we have a match.arg function for matching different string parameters, we can use the match.fun to make sure that we're using the appropriate function. So match.fun will take care of making sure that whatever is passed in here is an appropriate callable function. And then I can just call this function like so. Go ahead and create this version. And so now again, the default will be to use the median, but I can also pass in the mean. The nice thing about this match.fun function here is it'll also match strings to the appropriate function if it can find them. So I can specify mean, either the actual function, the string mean will also get matched to the appropriate mean function. And this also means I can pass in other things that aren't necessarily a good idea. Like let's say I want to impute with the maximum, which doesn't necessarily make sense, but I can do it. Or say the sum or something like that. So it just makes this function even more flexible than it was before. All right, so let's now talk a little bit about functional programming. So in R programming, we really emphasize the use of functions. And in R, that usually means relatively what we call pure functions, where in programming, a pure function is something that just takes an input, returns an output, does not have any side effects. So side effects means that it doesn't change anything elsewhere in the program. A function doesn't change any other things in the program. It just takes input, returns an output, and for a given input, you're always going to get the same output. So that's what kind of a pure function means in programming terms. And many functions in R are kind of designed to be pure functions where we map input to an output. And there aren't too many functions in R that we would rely on for side effects. So things that they do besides just computing and returning a result. An example of an R function that we use for its side effect would be something like print, or cat, or message, things like this, or plot. Plot is a good example. Plot has the side effect of displaying a plot. So that's an exception to this kind of idea. So in functional programming, we rely primarily on functions that map input to output, that don't rely on any side effects like changing their input. And functions are used really solely for the result that they return. So part of the idea here is that any function call can be replaced with the value that it returns, and the code would be the same. And for this purpose in R, pretty much, well, not quite all, but most objects in R are treated as what we call immutable. So that means the objects cannot be changed. This is not strictly true because obviously we can assign new values into a data frame or into a vector. But R has what we'll investigate later is a copy on write behavior to make sure that if we assign the same object to two different variables, if we assign into one of them, the other object is not going to see those changes. So they're going to become two separate versions of the same thing. So objects are treated as immutable. That means when we pass an object to a function, it's not going to be able to modify the input. If a function tries to modify one of its parameters, it's really just going to be creating a new object, essentially. And kind of following some of these ideas, some of these paradigms, makes it a lot easier to reason about our functions and about our inputs and outputs. So if we rely on pure functions, so mapping input to output, not relying on side effects, objects being immutable, so not expecting arguments to be modified, instead just relying on returned values, that's going to make it easier for us to reason about our functions, reason about inputs and outputs. It makes testing and debugging a lot simpler if we don't have to worry about side effects. And a nice trade-off or a nice payoff for this is that parallelization is a lot easier with pure functions rather than functions that rely on side effects. So this makes, we'll see, parallel programming is not necessarily the easiest to do in R, but relying on functional programming in this way makes parallelization a lot easier than if we were not relying on some of these functional programming concepts. Another feature of functional programming are what we call functionals, or higher order functions. Many of you have probably used these already, even if you're not sure what they were called. Basically, a higher order function or functional is just any function that either takes one or more functions as input or returns a function as a result. So if you've used R for very much, then you've probably already used one of these higher order functions or one of these functionals. And so the very popular apply family of functions is a family of higher order functions. And the idea behind these functions is to just apply a function over elements of a list. And this is the typical way that we approach things in R rather than using for loops. Many of you have probably seen this already. So for example, if we have a list and we want to get the sum of every element of the list, then rather than writing a for loop where we iterate over each element, sum it up, instead we can use one of these apply family members. In this case, I'm showing vapply. We give it the list, we give it the function that we want applied to each element of the list, and then it will return the result as a list. Let me jump back over to RStudio. A few more things here that I've skipped over because they're a little bit just for time, but you have some additional code notes here if you want to take a look yourself later. So I'm going to go down here and write one of these higher order functions that we were just talking about. So I'm going to create a function called add val. And so the idea behind this function is it's actually going to return a function. So I'm going to write a function that returns a function. And the function that it returns is just going to have the purpose of adding some value to whatever its input is. So this will make much more sense once I actually run it. So I'm going to call this function add val. It has one parameter called val for value, and it's going to return a function that also takes one parameter called x, and it returns x plus val. I'm going to run that. And if I just call add val with say 10, well, it's going to return a function. So let me go ahead and assign that to a variable. I'm going to call it add 10. And if I call this new function add 10s to say 2, well, it's going to add 10. So it's going to return 12. Say on 15, it's going to return 25, and so on. And so the neat thing here that's happening, well, there's kind of two neat things that are happening. Firstly, that we're returning a function as a result, so we can kind of create functions that are adaptive in different ways. And then also that this add 10 function that was created by the add val function knows what val is, knows this value. So it keeps track of that value. But where does that value actually exist? It's not in the global environment. And so this is where this lexical scoping and environments comes in. So in the context where add 10 was created, it was created inside of another function, inside of a function that has val as a parameter. So val exists as a variable inside the environment of this function. And so the function that's returned, add 10, has an associated environment where val exists. So if I look for the environment of add 10, it's this weird kind of a code. It's just the address for where this environment is stored. Well, we can notice that's different than my original add val function. That's the global environment is the environment for that, which is just where our own kind of where we're working, our kind of current workspace. But this weird environment that's associated with add 10, let's see what's in that. So I'm going to use ls to list variables in that environment, and that's where I can see val. And I can access that variable in the environment directly. I can see, oh, hey, it's 10. So that's one cool thing that we can do with functions and functionals. And so this is creating what we call a closure. So a closure is just a function that captures its environment. So really all functions in R are what we call closures. So they have access to any variables that exist in the environment where they were created. And they keep those variables around with them in that environment, even after that environment may not be pertinent anymore. So this was a temporary environment that was created when I called the add_val function. And even though add_val is finished executing, that environment still exists because it's being used by this add10 function that I've created. Then last thing I'll show here is another use of these higher order functions or functionals in a context where many of you have probably seen it. So here I'm going to, if I have a list and I want to say sum up every element of the list, I can use one of these apply family of functions. So here I can sum up the different elements of X, for example. So there's a few questions that I'll take a look at. So first question that's directly related to what we were just talking about. So will ls ... some crazy environment show you all variables in the functions environment? Yes. So that is, so ls is a function that will list all of the objects in any given environment. So the default will be to list all of the objects in the global environment, which is basically our default workspace. But I can do the same thing with any environment. So there's actually a few, some environments we have access to. So for example, the base environment, see what's in the base environment. So this is, so the base environment is something that's kind of loaded when we start R. It has a lot of things such as the addition, the arithmetic operators, lots of the operators we would expect as part of R, lots of the basic functions, and so on. Yes, so we saw, if I look at the environment for add10, I can look up what variables exist in that environment. If I created another, say, I'm going to call this add20. So this is going to have a different environment. You can see that these are different environments by comparing these codes. And so if I look up the environment for add20, you can see what variables are there. It's again a variable called val, but this is a different val than the one in the add10 environment. And in fact, if I say add a val variable to my global environment, well, here, so val is 99, but if I do add10, so say 5, it's still going to get the correct val because it has its own val in the functions environment that it's going to take greater priority than the one here in the global environment. All right, let's see. So that's kind of a quick introduction to writing functions, some of the things to consider when writing functions, as well as some kind of advanced, I'm not going to quite say tips and tricks, but because none of these are really tricks, but just some neat ways of making functions more flexible, some of the inner workings of how these functions work, and things like that. Any questions on these topics before we move on? And again, I know I could take much more time talking about functions, but we have a number of different topics that I want to cover, and I'm sure you want to see as well. All right, so let's go ahead and take a quick break since we're about an hour and a half in. After this, we'll talk about object-oriented programming. We'll talk about performance and debugging, and then we'll talk a little bit about scalability. So I'm going to take a quick break to refill my coffee, stretch. So please do as well. It's 12:36. We'll start again at 12:40, so about 4 minutes. And I'll be right back. I'll start again in just a moment. Give people a chance to return if they went to the bathroom or went to refill a drink. All right, so let's now talk about object-oriented programming in R. So here we'll first talk about what is object-oriented programming and kind of why you should care. We'll very briefly cover S3 because it's everywhere in base R. But if you do end up wanting to develop your own package at some point, if you want to submit to bioconductor, which if you're in mass spectrometry is probably what you want to do, we'll focus a little bit more on S4 since S4 is widely used on bioconductor. All right, so first, what is object-oriented programming, or OOP. So to recall that part of that quote from John Chambers, so everything that exists in R is an object. So every object in R, in addition to, well, being an object and existing, has what we call a class or a type. So an object's class basically just describes what kind of data it is, what type of object it is. So for example, is it a character vector versus a numeric vector? Those are very simple examples of classes or data types. So something that we can do is specialize functions for handling different types of data or different classes of data. And this is something that you've probably already used again, even if you weren't necessarily aware of it. So an example of this is the plot function. So this is just the base R plot function. So here we have 3 different versions of the plot function being called in different ways. So here, first we're just calling it on a data frame cars. Here we're calling it on 2 columns of the cars data frame. And here we're specifying a formula and then the data set. And as you can see, so let me jump over here to the object-oriented programming R Markdown document. So you only plot cars. So this cars is just a speed and stopping distance of various cars. So so we have speed on the x-axis, distance on the y-axis. And if I just do plot on the cars data frame, well, it's going to plot the first 2 columns of the data frame on the x and y axes. I could do that explicitly like this, or I could specify it using a formula like this. And all of these is going to give me the same plot, but I called these functions in very different ways. So the first one, I'm giving a data frame as the first argument. And the second one, I'm giving a vector as the first argument. And then this third one, I'm giving a formula as the first argument. These are all very different data types. They're very different ways of calling this plot function. And yet the plot function is able to handle all of these, as well as more. So how does the plot function actually know how to do this? If you're not aware of object-oriented programming, you might think that there's a very complicated if-else tree where we have if cars equals data frame, else, or excuse me, if x equals data frame, else if x is a vector, else if x is a formula or something like this. But that would be very complicated and not a very easy function to maintain. And it would be a very long function. So there's a better way of doing this rather than just one big plot function with a lot of if-else statements in it. And so this is where object-oriented programming really comes in. We can use object-oriented programming to specialize functions for handling different kinds of data, or in this case, different classes of object. So object-oriented programming is really just a way of organizing data and code built around some specific concepts. So we have a concept called the class of an object. So a class is just essentially a definition or blueprint for a type of object or a type of data that we want to represent. So a data frame is a class, a factor is a class, a matrix is a class, and so on. An instance is a specific case or a specific realization of that class of object. So here, so cars is a data frame. Data frame is the class. Cars is the instance. Cars is an instance of a data frame. And then we have methods. So methods are just essentially functions that can be specialized for different types of objects. So here Plot is just a function, but we have kind of invisibly, we have different plot methods for data frames, for vectors, and for formulas. So we can use a different method to specialize according to the class of object that we receive. So why use object-oriented programming? So we just saw that we've really already been using object-oriented programming everywhere in R. If you've ever programmed anything non-trivial in R, then you've used object-oriented programming. So data frames, of course, matrices as well. The big M matrix in the big M matrix class, if you've used the big M matrix package. Summarized experiment in bioconductor. So there's many different classes in bioconductor for containing many different kinds of experiments. So summarized experiment is one. In my Cardinal package, we have an MS imaging experiment as a class for holding mass spec imaging experiments. But every object in R has some kind of class associated with it that defines what type of data we're storing, how we're storing it, and so on. So these specific features of object-oriented programming that we have are a class, which is just a blueprint for how we're organizing a particular type of data. So a data frame is an example of a class, and a data frame is defined as storing tabular data organized into rows and columns. An instance is a specific case of a class, a specific object that belongs to a class. So Iris, the Iris data set, and the empty cars and the cars data sets are all instances of the data frame class. Inheritance is something that we can use to allow to further specialize different classes. So we can have subclasses that specialize superclasses. You might also hear we can have child classes that specialize parent classes. So an example from the tidyverse, if you've used, say, ggplot2 or dplyr, you've probably used a tibble before. A tibble is just a specific kind of data frame. And a tibble inherits behavior from a data frame because a tibble is just a subclass of data frame. And then a method is a function that is specialized for a specific class. So for example, we talked about plot. Plot is what we call a generic function. So it's a function that can be specialized to different classes by implementing what we call methods. So we have different methods for plot depending on what type of object we give to plot. There's different ways that different languages implement object-oriented programming. So if you're familiar with a language like, say, Python or Java or C++, then the way that R implements object-oriented programming is going to look a bit different. If you're not familiar with those languages, then don't worry about it. But R uses a very functional style of object-oriented programming. As we said, R is a functional language. And so the way that R uses object-oriented programming is we have what we call generic functions. So we have functions that exist to be specialized by different methods. So plot and summary are examples of generic functions. So these are functions that have a broad enough definition of what they might do that we're probably going to want to do something different depending on what kind of data they get passed. And so we can then implement different methods that belong to those generics. So for example, there's a plot default plot method. There's a plot method for formulas, a plot method for data frames, and so on. There's a default summary method. There's a summary method for LM, linear model objects, and so on. And we can just call these methods like ordinary functions. So we don't need to know exactly what the method is called. We can just call plot, or we can just call summary. And so in R, there's two object-oriented programming systems. There's S3 and there is S4. You can kind of tell that these names come from where they're originally implemented in the S language. So they're corresponding to different versions of the S language. And so S3 is the older object-oriented programming system. It's a bit simpler, and S4 is newer, and it's a bit more formal and complex. So S3 is used widely within base R, as well as a lot of CRAN packages. It's a more simple object-oriented system. It doesn't have any formal class definitions. We'll see what I mean by that in a moment. And it's also what we call single dispatch. So it can only specialize on the first argument that's passed. And again, we'll see what that means in a little bit more in a moment. S4 is a newer and more formal system of object-oriented programming. So this is what Bioconductor largely uses, as well as most Bioconductor packages. So S4 has more formal class definitions. So that means in S4, we kind of explicitly define what a class looks like. We explicitly say an object of this class has these specific components to it. For it to be a valid object, it has to pass these specific checks, and so on. S4 is also what we call multiple dispatch. That means it can specialize. S4 methods can specialize on multiple arguments. So where these systems typically get used, S3 tends to get used for simpler data structures in base R and CRAN packages. So a lot of the objects or classes in base R, like the base R data frame, base R matrix and stuff, these are S3 packages. Whereas S4 is going to be more common for complex data structures like you find in Bioconductor. So I'm going to first briefly talk about S3 so you know kind of that it exists and what it is when you see it, and then we're going to move on to S4. So with S3, as we said, there's no formal class definition. Basically, it's just defined by a class attribute. So any object in R can have what we call attributes, and there's a special class attribute that defines what class an object is. And any S3 class will really just extend a base R type. So whether that's a list, character, integer, double, so on. So an example of this is a data frame in R is an S3 class that just extends the list class. So for example, if I jump over here to our studio, so cars, if I look at the class of this cars data frame, well, I can see it's a data frame. But if I kind of look a little bit deeper, it's really just a list. So the base R type of cars is really just a list. And that's because data frames are really just implemented as an extension of lists that follow certain rules. And so they inherit certain behavior from lists. So if we want to access the first element, that's really just the first column. The second element is the second column, and so on. So there's no third column here, so I get a subscript out of bounds and so on. And then the way that S3 methods are implemented, they really just follow this naming scheme of the name of the generic function dot the name of the class that it's being implemented for. And so what that means is that it's relatively easy to find the methods for a particular generic function. So for example, plot, if I just type plot dot in our studio, it's going to show me a bunch of different methods for S3 methods for plot that already exist. So there's a default plot method, a plot method for functions, a plot method for time series, and so on. Let's see, probably I'll get the same thing if I type summary. So there's a summary for ANOVAs, a summary for data frames, a summary for dates, factors, LMs and GLMs, and so on. So I'm not going to go really into how to implement S3 because, again, I want to focus more on S4. But a lot of the objects that you'll find in base R are these S3 classes and have S3 methods defined on them. So again, some examples include data frames, the output of the LM method. We have LM objects, GLM objects, and so on. Any questions on S3 before we talk about S4? So again, the goal I wanted with S3 is just to give you an idea of what's going on behind the scenes. So when you call, for example, plot on different kinds of objects, you're aware that of how R is finding the appropriate plot method for that object. It's using this object-oriented programming system. All right, so let's talk about S4. So S4 has more formal class definitions. And so we have to explicitly define what objects of a certain class in S4 actually look like. So we can define different data slots that have specified data types. We can define a validity method to check whether an object is valid if it follows certain rules. And then we can define methods using the set method function, for example. And so some examples of S4 objects. So let me go ahead and load, for example, summarized experiment. So summarized experiment is a bioconductor package. And summarized experiment is an S4 class that is just used for a number of different, to represent really any kind of high dimensional data. So kind of, because bioconductor probably originally kind of designed with genomics data sets in mind, but also works for a number of things, including single cell, really anything with a number of assays or anything like that. So for example, if I want to create a summarized experiment object, I'm just going to run this example code. So RSE here is a range summarized experiment. So this is a subclass of summarized experiment. You can see it prints out in a certain way. I can see that it's, if I want to check what class it is, it's a range summarized experiment and so on. Question, when should you use S3 versus S4 and vice versa? So as far as just using these go as a regular user, you don't necessarily need to know too much about whether an object is S3 or S4. You'll probably know just based on where the package came from. So in base R and CRAN, S3 is going to be more popular. On bioconductor, S4 is going to be used for a lot of data structures. And the difference really is kind of how simple versus how complex that data structure is going to be. So S3 is easier to get started with because it doesn't have as much formalism behind it, because you don't have to rigorously define exactly what the data structure looks like. And so for simple purposes, S3 is going to be easier and faster to get started with if you're coding your own class. And so I would say often S3 is good enough if you're, say, returning a type of analysis and you want to make sure that you have, say, plot methods and summary methods that get that you can implement. So, for example, I mentioned the LM function and the GLM function. These return objects of class LM and class GLM, so that if you ask for residuals or try to plot them, you'll get something appropriate. Now, S4, because it has this more formalism behind it, is going to be more appropriate for more complex data structures. So, data structures that have kind of specific rules that they need to follow. So biological data kind of falls under this. So with bioconductor summarized experiment, we have a matrix that contains the actual either intensity data or abundance data or read counts or whatever kind of data we're working with. We have separate data frames for holding the phenotype data as well as the feature metadata. So we have separate data frames for holding metadata about either the rows or the columns of that main matrix of intensities or abundances or read counts or whatever. And so we have to make sure that these different parts of the data structure are following certain rules. And so that's where S4 becomes more useful. Question about S6. So I would assume that's probably R6. I don't think there's an S6, but there is a package that implements an object system called R6. I think that's used largely by the RStudio team. So there are a couple other object-oriented programming systems that do exist. So there's R6 and there's reference classes. So R6, I believe, comes from RStudio, and reference classes are built into R by RCore. So these are other types of object-oriented programming systems that implement a more kind of traditional object-oriented programming approach, similar to what you would find in, say, Python or Java. And that is the objects in those systems capture state. They are mutable rather than immutable. So S3 and S4 classes, instances of these classes are going to be immutable, which is kind of the rule in R. Objects tend to be immutable, except for environments which are a little bit strange. The R6 and reference classes exist to implement a mutable version of object-oriented programming. These are largely used for things like programming GUIs, graphical user interfaces, and other things that require state. So that's where these other systems like reference classes and R6 will tend to be used. I would not suggest using them really for data analysis. So for data analysis, we'll probably stick to S3 and S4. If you have an interest in programming, say, graphical user interfaces, other things like this, or have other use cases that require mutable state, then that's when you would look into reference classes or R6. So here's just an example of an S4 class implemented kind of from scratch. So here, for example, suppose we want to create an animal class, and we have a cat and dog class that can inherit from the animal class. Because cats and dogs are both animals. They're both subtypes of animals. So it makes sense for cat and dog to be subclasses of a more broad animal class. So here I have a set class function call. So this is what is going to create the class definition. This is not something that would appear for an S3 class, but S4 is more formal. So we formally define the class. So it's going to be called animal4. I'm just using that to distinguish from the S3 version I have earlier if you want to look at it later. It has a slot called name, which is going to be a character. So these animals have names. And I have a validity method to check whether this is a valid instance of an animal class. And all this is going to check is check that the object name is length 1. So this is what defines the actual class. Here we have 2 more set class function calls to create the cat and dog class. The contains here, this indicates that these classes inherit from the animal class. And then once we've defined these classes, we can create new instances of them using the new function. But generally, we want to create a kind of official constructor function so that users, rather than calling the new function, will call our constructor function. So here I'm creating a constructor for cats, and it's just going to take in the name. It's going to call this new function to create a new instance of the cat class, and I'm going to call this constructor cat or cat4. And so I can use this constructor, create a new cat called mittens, and then here I'm creating a method called speak so that the animal, or in this case, the cat, can speak. So let me jump over to RStudio. Let me go down here. So here I'm going to create the animal class. So this is a virtual class. That means that I can't have instances of animal. So I need to specialize this class further by creating subclasses. I can't just create an animal. I have to say create a cat or a dog. So here I'm going to create cat and dog. These inherit from animal. And I'm going to create constructors for them here. So here I have Mittens and Duke. These are my cat and dog objects. So something that is useful to create is to create a print or a show method. So in S3, we would implement a print method. In S4, for whatever reason, we implement a show method. So I use the set method function to implement the show method. Here I specify that I'm implementing it for the animal class. And then I'm just going to print out the name of the animal. So note that this show method is being defined for animal, not for cat or dog. But if I look at one of my cats or dogs, they're going to inherit that behavior from the animal class because cats and dogs are both animals, so they're going to still use this show method to print out their names. So here I'm going to create a new generic method called speak. I'm not going to get into exactly what this is doing, but this is just how we create a generic an S4 generic function. So speak here is basically just a generic function, which means that we can implement different methods for it. And so here I'm going to create methods for cats and for dogs. So cats are going to go meow, dogs are going to go woof. So here are the different speak methods that I've implemented. So I have a speak method for cats and for dogs. And I'll go ahead and implement one, a default one as well. So here I have a method for animals and a default fallback for anything. So now if I call, say, speak on a list, I'm going to get this any method. So this is the default one, which is going to print out strange noises. And so down here, if I call speak on one of my animals, I'm going to get the corresponding speak method. So for Mittens, Mittens is a cat. So I'm going to get Mittens to say meow. For Duke, Duke is a dog. So if I call speak on Duke, Duke is going to go woof. And if I call it on, say, a data frame, I'm going to get my default method up here, any, which is just to print out strange noises. All right, so that's a very quick walkthrough of S4. So as I said, on Bioconductor, S4 is the common way of doing object-oriented programming. If you want to see a more complete example of an example S4 class, in addition to all the packages on Bioconductor, I have a kind of example package that I put together that's kind of simpler and easier to understand than if you went to just try to look at any Bioconductor package. So I call this MS example. So it's a simple package that shows some examples implementing classes and methods for working with mass spectra. So I'm going to quickly show that to you. Not taking too much time to look at it, but it's a reference for you to look back at if you want a more complete example. So this is a working R package, so you can install it if you want. Easiest way to do that would be the remotes package. Use the remotes package and then the install GitHub function. There's an example in this slide of how to do that, as well as here. Let me drop this in chat real quick. So the link's in the slides, but there's a link in chat as well to this GitHub. Look at the R code. So I have a few classes that I've implemented. So in particular, I have a mass spectrum class. So this is an S4 class that just implements, contains a mass spectrum. So the slots, it has an MZ slot. So this is a numeric vector with the mass to charge ratios, an intensity slot. So this is a numeric vector that contains intensities, is centroided. So this is a logical, so a Boolean value indicating whether it's centroided or not. And then peaks here, this is going to be an integer vector giving the indices of any peaks in the mass spectrum. So here I've implemented a validity method. So this mass spectrum, I expect this object to follow certain rules. So for example, I expect the mass to charge ratios to be sorted in increasing order. I expect to have the same number of mass to charge ratios as I have intensities. I expect any peak indices to be within the range of the number of mass features in this mass spectrum, and so on. Here's the constructor for this. So you just pass in a vector of masses and intensities, specify whether it's centroided or not, and then it'll create a new mass spectrum object. Then I have some methods implemented for this. So some basic accessor methods. So another thing that we typically do with object-oriented programming is to have what we call accessors or getters and setters. So rather than accessing the slots or the components of an object directly, so with an S4 object, you would use the @ symbol if you wanted to directly access the different slots. But as a user, you shouldn't do that. So instead, we implement these accessor functions. And the idea behind this is that other people will use these accessor functions. And so that means that even if the internal structure of the class changes, then the accessor function can be updated to still do the correct thing. So maybe at some point I decide to change this internal intensity slot from calling it intensity to calling it intensities or something. But I still want intensity to work as an accessor function. Then I can do that. So that's one thing to keep in mind when working with S4 classes, is to make sure that you're using the accessor functions to access the different components of an object, rather than trying to access the slots directly using the @ symbol. That's one kind of common mistake that I see when people first start using S4 classes, which again are everywhere on Bioconductor, is to try to access the slots directly using this @ symbol. But you shouldn't do that, because if the internal structure of that code changes, it can break your code. Or else, ideally, if you're using the accessor functions, then these will be updated so that they continue to work. All right, anything else I want to show you here? So I have a plot method here, so you can plot mass spectra and so on. All right, so that's what I wanted to cover in terms of object-oriented programming. Are there any questions on that? And again, I realize that we're not covering these things in as much depth as we could for the sake of time. So we still have time to talk about performance and scalability and such. So any questions before we move on to performance profiling and debugging? Right, I see a useful comment, but no questions. So that's a useful comment about the Bioconductor conference that's coming up in Seattle and virtually. Maybe one of the TAs can copy that to chat. Okay, so let's talk about performance profiling and debugging our code. So we'll first talk a little bit about performance. We'll talk about timing our code, and then we'll talk about some debugging tips. So R is sometimes considered slow. To an extent, this is true because R is an interpreted language. So is Python. Ultimately, just about any interpreted language is going to be somewhat slower than a compiled version. And the reason for that is because interpreted languages like R and Python run on an interpreter rather than being compiled to native code that can run directly on the CPU. So C, C++, Fortran, these can be compiled to native code so that they'll run much faster. R and Python, these run on an interpreter, so they tend to be slower. The trick, I suppose, is that lots of R and Python functions are written using C, C++, or Fortran, or one of these other more performant languages. So when we talk about R being slow, it's really not much slow. It's not any slower really than any other interpreted language like Python. The important thing is really just figuring out how to write code so that it's fast, and often that means figuring out how to write code so as much of the actual computations as possible happen in a more performant language like C or Fortran or C++ or whatever. And usually that means vectorizing code, but not always. We'll see. So as I brought up when we were talking about functions and writing functions, you never really want to prematurely optimize. So when you're writing a function, focus first on implementing it correctly. And then if you find out that it's too slow, only then should you really try to make it faster. So that means benchmarking it and actually seeing if it's slow and comparing it with alternative implementations to see which one really is faster. Because sometimes what people think will be faster isn't necessarily going to be faster. So first, write correct code. Lots of times it's going to be fast enough. You can always go get a coffee while it runs. And if you're ever unsure, just benchmark it to confirm if it's being too slow. So I'm going to consider a case study here of finding local maxima, the goal being finding peaks in a mass spectrum. So this is going to be using some of the code from the MS example package that I just showed you. So if you want to run this, you would need to install it. Again, you can do that using the remotes package and the install GitHub function from that. There's a that's in both the README of the GitHub page as well as in the previous set of slides. So here I've created a simulated mass spectrum from my MS example package and plotted it. So this is what the mass spectrum looks like. And the goal is to find all of the local maxima in this mass spectrum. Now, we're not concerned right now with labeling them peaks or not, so I'm not thinking about signal to noise ratio or anything like that. All we're looking for right now is local maxima. We'll leave it to a later step to decide whether they're peaks based on signal to noise ratio and stuff like that. So right now we're just implementing local maxima finding. So I'm going to show you a couple different implementations of a function. So here is version 1 of my attempt to write a function for finding local maxima in a mass spectrum. So it's going to take x, which is going to be a numeric vector, and a parameter called half window. So this local maxima algorithm is going to work by just basically sliding a window through the mass spectrum and checking whether the intensity that we're currently looking at is the largest intensity within this window. So that's what this half window is defining. It's defining the size of the window. So half window being 2 means we're going to be looking for any intensity. We're going to be looking at that intensity and the intensities, the 2 intensities to the left and to the right of it. So basically a window of 5 intensities. And so the way this works, we're going to, so what I'm doing here is first I'm seeing where I'm going to start and where I'm going to end. So I can't, because I'm using a sliding window approach, I can't start at the very first intensity because that window would include empty missing values. So begin and end here are the intensities where I'm actually going to start looking, the indices where I'm going to start looking. Starting at begin, ending at end. So these are just indices where I'm going to look. Out is going to be the, I'm going to ultimately return out as an integer vector giving the indices where I found local maxima. So first thing I'm going to do is going to check, does my beginning and end happen, is my beginning less than 1? Is my end greater than the length of x? If so, that means my vector is shorter than my window. So I'm just going to return an empty integer vector because there's no peaks in that. Otherwise, I'm going to go into this for loop. So I is the current index that I'm looking at. I'm going to go from beginning to end, iterating through this vector. Here, I'm just getting the indices of the little window area that I'm looking at. I'm going to start by specifying, by assuming that this is a local maxima. So isMax is true. I'm setting isMax to true. Then I'm going to loop through the window that I'm looking at. And if I find any other intensities greater than the center one that I'm inspecting, then I'm going to set isMax to false. After doing that little for loop, I'm going to check if isMax is still true. If it is, then the current index is a local maxima. And so I'm going to add that to my out vector of integers that I'll return at the end of this function. All right, so let me jump over to our studio. Close this. And run this. Actually, let me quickly restart R since I have a bunch of stuff from previous sessions. So, all right. All right, so here's a simulated mass spectrum. Here is that current implementation version that we were just talking about. I'll go ahead and run that. And so here is what I get when I run this. Let me go ahead and try to highlight where these are occurring. There we go. Oh, okay. Well, that's a lot of local maxima. So maybe I won't. So maybe you'll just trust me that this does work. Maybe I can zoom in further, but I don't want to take too much time trying to check this super diligently. Let's say 400 to 450. All right, well, clearly there's a lot of false positives because we're not looking at any signal to noise ratio yet. But we can see, for example, that this little peak was selected as a local maxima, along with a lot of others that signal to noise ratio would get rid of. But anyway, so this is my first attempt at a local maxima algorithm. So let's go ahead and benchmark this to see how fast this runs. So I'm using a package called bench and a function called mark from it. So I'm just calling it as bench : mark. And so this will run my function multiple times. Specifically, it ran it 17 times. I can choose how many iterations I want. Let's run it 20 times. Is that how it? I guess it runs for a certain amount of time and it'll. Okay, not totally sure why it's not running at the exact number of iterations I'm asking for. But anyway, so here I'm just running this locmax implementation that I have, and it's giving me this timing. So It's important to have multiple iterations because your computer is doing a lot of different things at any given time. So from one run of a function to another, there might be some differences. And so we're going to look at the median amount of time it takes to run this function, which it happens to be 11.5 milliseconds, which is not too bad. That's pretty good. But this function might get called thousands upon thousands of times if we're processing thousands of spectra. So it is worthwhile to ask if we can do better than this. So,
Kylie, if I may interrupt, there's a question requesting you to repeat the plot function, the AB line plot.
Let me go back up here. So up here, what I'm doing is let me tighten this window a little bit. All right, so here I'm just plotting the output of my function. So I'm running this on the, I'll call this M. So I'm running this on the intensities from the first spectrum that I simulated. So M here, these are indices of where we found local maxima using this function. And so I'm going to just use this AB line function to draw vertical lines where this occurred. And so I'm using my MZ accessor function to access the mass to charge ratios from this first spectrum. So here MZ on S1, this is getting me the mass to charge ratios so that I'm plotting those AB lines, those lines at the right spot. So I'm subsetting these mass to charge ratios with the indices that locmax returned. So AB line V equals those mass to charge ratios is drawing these lines. So that's how I got here. And of course, we see again that there's a lot of false positives here, but we also see this one, which is clearly some kind of peak. And again, right now, we're just doing local maxima, not caring about signal to noise ratio or anything like that. All right, so our function runs in about 11.5 milliseconds. So not too bad, but let's think about some things that we can try to do to improve this function. All right, so jump back over to here. So here's version 2 of my function. And some of you can maybe think about what you would change to try to improve this. As I was describing it, some of you might have caught some things that could be improved. And so let's take a look at what I did. So a lot of this is going to look fairly similar. So I'm going to focus on just the differences. So one big difference is, if you remember before, I started by having out as just an empty integer vector. And then at every iteration, I'm checking if the current index is a peak or is a local maxima or not, and kind of appending to it using the C function. And this is a pattern that you see a lot with a lot of beginner R programmers, is just kind of trying to grow a vector like this. But in R, that's really not an efficient way to do things because all objects are immutable. So what this is really doing is it's allocating an entire new vector rather than really appending to an existing one. So something we can do right away to try to improve things is to initialize this out function or this out vector with the correct length. So here I'm using logical to to initialize this as a logical vector. So it's now going to be trues and falses rather than numeric indices. There's a quick question on the mass spec simulation function that I'm using here. Question, is it centroided or profile data? So this is from the, so I can show you in just a moment real quick. So this is from the MS example package. It's a direct copy of a similarly named function called simulate spectrum that's in my cardinal R package that is available on Bioconductor. But if you just want this function, it's also can be copy pasted through this MS example package. Just credit me. So it generates a profile spectrum by default. You can change it to centroid if you want. Either way, it'll generate a profile spectrum. If you ask for centroid, it'll just then only take the peaks from it. I think if I remember how I implemented it correctly. But anyway, it starts with profile data. You can specify different things like the standard deviation of the peaks, of the noise, all these different things. And it basically works just by creating Gaussian peaks, overlaying noise, simulating some mass shift and other things like this. But yes, it's available both here. You can copy paste it if you credit me. It's also available in the Cardinal package on Bioconductor as simulate spectrum from there. So no, let's go back here. All right, so one of the main differences here is that we're initializing this out vector with a logical vector of the same length as the spectrum. And so what that means is rather than trying to grow a vector, which is going to reallocate the same, it's going to reallocate a new vector each time. Instead, we can just assign into that pre-allocated vector. So that's what's happening in here. So we have the same inner for loop for the most part. But the difference is now, if we encounter other intensities larger than the current one, we can just immediately assign false here. So that's not a peak. That invalidates it as a local maxima if we find other intensities in the same window that are larger than it. So this removes that combine C function call. The other change here is this break. So previously we looped through this entire window, whereas here now we can go ahead and break out of this inner for loop as soon as we know that this is not a local maxima. To keep the output the same, so previously we were returning the indices, numeric indices. So here out starts as a logical vector. So I'm going to use which to extract the indices of the true values here. So if you call which on a logical vector, which will just return the indices of the true elements. So at the end, this is going to return the same output as the previous version. So those are the main changes in version 2. And then just to save time, we'll go ahead and look at version 3 as well right now before we benchmark these. So you might have heard at some point in your life not to use for loops in R programming. And so here I've attempted to remove any for loops from my code. So I've replaced the for loop with a call to vapply. So if you recall, vapply is one of these higher order functions from the apply family. So that means we give it a list or some kind of sequence and a function that we want applied to every element of that list. So I'm using vapply. I'm giving it a vector of indices that I want to apply this function to. vapply requires a template for what the output of this function looks like. That makes it a bit more efficient than lapply or sapply. And so the output of this function is just going to be a Boolean true or false. So here's the template of a length one logical vector. And then I return, this is going to return a logical vector. Inside, I have removed the inner for loop as well with a vectorized version. So here I'm subsetting the entire window that I'm looking at, seeing if any of the elements are greater than the central one. Any is a function that will return true if any of the elements are true. And so those are the main changes here. There's one additional change here, so I have to pad the output with some falses because, again, we're looking at a sliding window, so I'm not considering the intensities on the very ends. There's a question, are there any situations where for loops are your only option, such as iterating through S4 objects? So that's kind of what we're going to find out here. So as I said, you've probably heard to avoid for loops in R programming. I did not necessarily say whether that was the correct thing to do or not. So that's something we'll find out in a moment here. So there are definitely situations where where for loops actually do make sense. That's going to be generally anywhere where you can exit early if you are able to. So here we can exit early if we're looking through that window and find out that we don't have a local maxima. Markov chain Monte Carlo simulations generally need to be some kind of for loop if we're relying on anything that relies on a previous value. So anything that's kind of iterative and relies on the previous iteration is going to require some kind of for or while loop. So there are definitely situations where you have to use a for loop. But even then, even when you can remove a for loop, we'll see if it's always worth it. All right, so let me go back to RStudio, create this version 2, create this version 3. So before benchmarking them, we want to make sure that all of our functions actually return the same output, because if one of them is incorrect, then we don't want to consider it anyway. So here I'm just going to confirm that all three of these functions return the same output when run on the same spectrum. We got true for both of these, so all three of these are returning the same output. And so let's now go down here and try benchmarking on these three different versions. So just run this. All right, so probably thought to yourself that, I guess I didn't ask to think to yourself which one of these you think will be fastest, but if you listen to the oft repeated advice to avoid for loops in R programming, you might have ended up thinking version 3 would be the fastest because we got rid of all of the for loops. So version 3 has no for loops. We only use the vapply. So we are using the high order functions, functional programming, and vectorizing this window check. And so you might think that version 3 would be fastest, but here if we look at the median times, version 3 is actually the slowest. Both version 1 and version 2 are faster. So both versions with the for loops were faster, and version 2 happens to be the fastest. So version 2, on average, about 7.2 milliseconds. Our original version 1, still about 11.5 milliseconds. And then version 3 ends up being a little bit slower than that. So despite kind of the popular perception, for loops in R are really not inherently slow. So there's no real difference between using an apply function versus a for loop if you are doing it intelligently. So the main issue that people can run into with a for loop is doing something like this, where you're trying to grow an output, and R is not really good at growing vectors or anything like that. So that's the main time that for loops will tend to be slower. So the main thing that is speeding up code here is pre-initializing the output and being able to assign directly into it, rather than trying to grow a vector, which ultimately ends up in a lot of additional allocation of memory. So if we look at the memory usage here, we can see that version 1 has by far the most memory usage because it's reallocating that vector so many times. Version 2 has the least memory usage because we allocate the result beforehand. And then version 3 also does not have very much memory usage compared to version 1. So version 3, vapply will take care of the allocation for us. It'll return a logical vector as the result. Still ends up using a bit more memory than version 2. But the real loss in version 1 is that it's going to be slower because of the memory allocations. So the main lesson here, besides pre-allocating results if you do end up using a for loop, is to always benchmark your code if you're actually trying to optimize. So don't prematurely optimize. It's often going to end up being fine. If something does need to be faster, then make sure you benchmark it and compare the different versions rather than assume which one will be the fastest. Whenever you can, try to use functions that call C and C++ code. So in R, these will be primitive functions often. So things like mean, median, these will call down to C and C++ code. Row sums and call sums versus using apply on the rows and columns. So whenever you can, use specialized functions that can call down to native code. And vectorized functions rather than loops. So again, vectorized here does not necessarily mean an apply function. It means, again, like row sums or call sums rather than using apply sum over the rows or columns. And try to avoid making copies or duplications of objects. So that's the main problem that we had with version 1. So there's a little bit more here that I want to mention in terms of avoiding objects being duplicated. Some of this code may not work in RStudio because RStudio, I'll explain that in a moment. So as we said, one of the main things that saved us time with version 2 of our code was that we were able to pre-allocate the result and assign directly into it. So we were able to modify our vector in place without making copies of it. And so that is kind of the key, one of the keys to writing performant R code is trying to avoid unnecessary copying of objects. So for example, here we have X. X is a length 10 vector. If I assign into X, say, change one of the values, think to yourself what might happen. So there's kind of two options. Either X is going to be modified in place, or X is going to be copied, and R is going to modify the copy. So, so this may not match what I have in the code comments here, but we'll try it and see. So so we can find out a useful function for finding out when objects get copied is this trace mem function. And in my version of R, I'm able to use trace mem. In some versions of R have to be compiled specifically with memory tracing available, but at least on Mac OS, it comes like this already. So you can run trace mem on an object, and it'll print out a message whenever that object is copied. So here, for example, if I just call trace mem, it's going to start off by printing out the memory address of that object. And then I can assign into it, and trace mem will print out a message if that object is copied or moved. So in this case, it does look like X is being copied. And so we're modifying a copy of the object. We can see that because trace mem prints out this message. The original object is at this memory address, but a copy is being made, and now X is stored at this memory address when it was modified. So this is one thing that is going to show up a little bit differently in RStudio, because this behavior is going to depend on how many references there are to an object. And for better or worse, running this in RStudio is always going to be a little bit less performant, because RStudio makes a reference to every object in the global environment in order for this environment browser to work. So this environment browser that shows you what different objects are in your global environment, this is making an additional reference to X so that X can't be modified in place. Let me go ahead and pull up a version of this that is not in RStudio, so I can attempt to show you what it will look like outside of RStudio. All right, you should see a Sublime text editor and my terminal window. So I'm going to go ahead and run what I just ran before. So I'm going to run trace mem on X again. And let's try that assignment now. So this time X is mutated, is being modified in place because no message was printed out. And so that's because there's no other references to X. There's only one, the object that X references, that X is the only reference to it. So what happens then if I create another reference to X? So here, let me recreate X. I'm going to trace memory on it. And I'm going to assign X to Y now. So now we have an X, we have a Y. Both of these are referencing the same object. So now if I try to assign into X, I get a message from trace mem that the object has moved because it's been copied, because now both X and Y reference it. So in order to change X, we have to copy it so that Y remains unaffected. It's a little bit wider. All right, so yeah, so when there was only a single reference, we were able to modify X in place. Once there's an additional reference, then we're going to get a copy if we try to modify it. So there are some other situations where that can happen. So here, for example, X here now is an integer vector. Before X was a double vector. X now is an integer vector. I'm going to trace mem on it. And now if I try to assign a floating point value into it, I'm also going to get a copy. And in this case, that's because, well, an integer vector can't hold a floating point value. So we're going to make a copy of it and elevate the object to a double vector. And so in this case, that's what results in the copy being made. So previous versions of R, so this is one of the big changes between R4 and previous versions of R before R 4.0, is that R now uses true reference tracking, which means that, say, if I go back up here, let me create X. Let me assign X to Y. So right now we have two references to the object. Now, if I remove one of them, let's remove Y and try to assign into X now, you can notice I didn't get a message about X being copied. So that's because R 4.0 and newer now has true reference counting, which means that when I remove that reference of Y, so for a moment, X and Y were both pointing to the same object. I removed Y from the global environment. So now X is the only reference to the object. So that reference count is able to go back down in current versions of R. That did not happen before. So in older versions of R, as soon as there were multiple references to an object, it would always get copied, even if we got back to a point where there was only one reference to it. So that's one major improvement that R 4.0 and newer has to memory usage. One other quick point I'll make here is with complex objects, this gets a little bit more complicated. So for example, say we have a data frame. Well, there's multiple parts to a data frame. There's the actual data frame itself, so the kind of overall container, and then there's the individual columns. So I'm going to trace memory on both of these. So I'm going to trace memory on X, the data frame itself, as well as the first column of the data frame. And now I'm going to go and replace the second column. So I get a couple trace mem messages. Both of these are resulting from the same object. The data frame itself is being copied. So this might seem like a big deal because you don't want to copy an entire data frame to change a single column. But you'll notice that, again, both of these messages are referring to the same object. So this address is the same as this address. So this is just referring to the container, the outer data frame. You'll notice that the address for the first column doesn't show up at all here. So the other columns, apart from the second column, don't actually get copied here. So R is creating a shallow copy of the data frame, which means it's only kind of duplicating the outer container. It's not actually copying all of the data within the data frame. So that's relatively efficient. So this isn't actually as big of a problem as it seems because the actual amount of memory or amount of data that's being copied is relatively small. It is not all of the columns. Let's see. Yeah, there's a little bit more to this, but I think that's all I want to say on that at this point. So since we're running out of time and I want to at least touch on the last couple topics. So quickly, I want to talk quickly about debugging R code. So as you start writing more complex code and implementing functions, at some point you'll need to debug your own code to figure out what the error is. And especially when that code is inside of a function, that can potentially be a little bit more difficult than trying to debug a regular script where you're not writing your own functions. So here's just a list of some useful debugging tools in R. So lots of times you're writing a function, there's a bunch of function calls inside of that function. And so when you see an error, you're not always sure where that error came from, which function actually generated that error. And so as a first step, looking at the traceback can be a good way of finding out where that error occurred. So, for example, suppose here, so we have a number of different functions. So here we have 4 functions, f, g, h, and I. I'm calling the function f, and I get an error. So A plus D non-numeric argument to binary operator. All right, well, if I look at f, well, my f function is just calling the g function. So if I only have my function f that I'm writing and g, h, and I are in some package maybe, I don't necessarily know where this error is coming from, because this code that I'm seeing, the string a plus d, doesn't appear in my function f. And so it can be useful to know what the traceback was at the time that that error occurred. And the traceback is just what functions were being called and what function was the last function that we were in. And so the traceback looks like this. So f called g, called h, called I, and I is the function where that error actually occurred. So that's a useful kind of first diagnosis of knowing what function actually caused the error. RStudio has a nice little show traceback option to show you that whenever you get an error as well. And then beyond that, there's some other useful functions. So once you know where an error might occur, if it's in one of your own functions, you can add a call to browser. Browser is basically a debugger. It's going to enter the R debugger. And so go back to, let's see. So let me just go ahead and modify the I function here. I'll add in a browser call here. So if you can modify your code where the error occurs, you can put in a call to browser. And browser will drop you into R's debugger. So you'll see this browse thing. And within the debugger, what that means is you can inspect different variables that exist inside the function environment that you can't access from outside. So right now here, I have one variable d. Its value is 10. And so I can see clearly if I try to add a to 10, that's not going to work. And if you're doing this in RStudio, RStudio will also give you some nice buttons that allow you to control the debugger. So next means execute the next line. Continue means continue the evaluation. Stop means get out of the debugger, and so on. So that's a really useful option if you want to kind of get inside of a function while it's being evaluated and inspect the variables within that function's environment. That can be difficult to do from outside. You can, it's a bit more interactive than like adding print statements to try to figure out what the values of functions are. Another option is to use options error equals recover. This is useful if you don't necessarily have access to the source code to add in a browser call. And this just means that as soon as an error is occurred, it enters that debugger. You can also use debug and undebug on specific function calls. So this means enter the debugger on a particular function call. So some examples of that. Let me get rid of this. So here, for example, I can call debug on I. And so if I call F10, once we enter the I function, once I function gets called, it's going to jump into the debugger. When you're done debugging a function, you want to call undebug on it. Here's the options error equals recover version. So now if I encounter an error, it'll print the traceback, and you can choose which function to enter. So if I go into the I function again, you can see there's my D variable and so on. To stop that option, you can do options error equals null to turn off that debugging. So some general tips when it comes to writing R code. In terms of writing code that's going to be easier to debug and maintain. Some general defensive programming strategies to use. Fail fast and fail early. So that means you want to catch any potential errors as early as you can. So check whatever inputs you're getting. So if your function takes parameters, make sure those arguments actually make sense rather than just assuming that they make sense and passing them along. Again, short, simple functions that do one specific thing means those functions are going to be easier to debug. Avoid trying to use non-standard evaluation. It's probably not a danger for many of you because we haven't talked too much about it. Again, this is something that's used widely in the tidyverse. That makes those functions difficult to debug, yeah, it's just avoid non-standard evaluation. And if you're not sure what that is, then you're probably good. Avoid, this kind of falls back into the short, simple functions when you can. So avoid overly flexible functions. So if you're trying to handle too many cases, that can make debugging difficult. I mentioned how we were talking about object-oriented programming. I envisioned this version of the plot function that just has a lot of if-else statements for handling different kinds of objects. That would be a pain to debug. So instead, if you find yourself trying to write a very flexible function for handling lots of different cases, think if there's a way that you can use a strategy like object-oriented programming with different methods to accomplish that instead. All right, there's more in the R Markdown document if you want to look at some more examples, but for the sake of time, I'm going to try to quickly share a little bit about scalability before we run out of time. All right, so let's jump over here. So again, because we're almost at time, I think I'm just going to walk through the slides and to show you kind of what tools are available rather than running the code, which you have access to in the R Markdown document, so you can run that yourself later. So my goal here is just to at least introduce and expose you to some of the options for scaling your code up to larger data sets if you're working with very large data. So I'll first mention about parallelization, and then we'll talk a little bit about big data backends. So let's start with parallelization. So parallelization is easiest when you have what we call embarrassingly parallel problems. That means a bunch of independent tasks that require no communication between them. And so this means that you have data that can be split into independent subsets. And this basically means anything that could be performed with an lapply or any other member of the apply family. So this does not necessarily apply to, again, iterative processes like an EM algorithm or a Markov chain, other things like things that rely heavily on stochastic stochastic things in an iterative process, things like this. So these are more things that you can do with an lapply, where you can just split up the data and apply the same function to every part of the data set. These are good candidates for parallelization. So on Bioconductor, which I recommend that you use, there is a package called BioCParallel, and it provides a function called bp-lapply. And this is essentially just a parallel version of the base lapply function. It's especially nice because it can still run serially, even if you don't want to run it in parallel. And so this is kind of the easiest way to get started with parallel computation is whenever you have something that can be done with an lapply, just use BP lapply instead and register a parallel backend. So there are different parallel backends that you can use with BIOC parallel. So there's a serial backend. So this is used if you just want to run something, I guess, normally in serial, so non-parallel execution. This is useful as a fallback if someone doesn't want to use the parallel version. It's also necessary if you want to debug your code. So you cannot debug something that's running parallel. So you can't run a debugger in one of your other R sessions that's running in parallel. You need to run it serially if you want to be able to use any of the debugging tools that I just talked about. If you are running something in parallel, then there's two primary backends to be aware of. So there is what we call the SNO backend. So this stands for Simple Network of Workstations. This is a backend that's available on any operating system. So it creates a cross-platform cluster. Cross-platform here meaning any operating system. So this works on Windows, Mac, Linux, any of these. And it works by starting new R sessions in addition to the main R session. So it starts additional worker R sessions and then transfers the necessary data to those other worker sessions and runs whatever code on those additional R sessions. The drawback here is that it takes a little time for those additional R sessions to start up, and it also takes some time to transfer the data to those other R sessions. Question, have you run into any implementations of RO Bioconductor that utilize GeForce graphics processing units? I have not personally used any R packages that use GPUs. I would think that you could probably use a version of R that might be compiled with a BLAS or LAPACK that might use GPUs. I know that you can call some Python packages like with Keras and TensorFlow that can use GPUs, but I'm not sure of a way to directly utilize GPUs from R. You can, of course, call C and C++ code from R. So if you're writing some kind of some either CUDA or OpenCL code that you can call through C or C++, there's probably a way to get that working. Getting it to work out of the box is a bit still of a challenge. Certainly GPUs can be much faster than CPUs, but it is certainly harder to program on them. And again, yeah, cross-platform solutions are still a bit of a challenge. So I don't have a great answer to that. If someone else has more experience with trying to get GPUs to work with R packages, then you can go ahead and chime in at some point later. All right, so SNO backend is one of these options. Multi-core is another option. This one is specific to POSIX compliant operating systems. So this includes Mac OS and Linux. This will be faster than the SNO backend because it clones the original R session. So it has less overhead of starting up the additional R sessions, and it can share the same data as well. There's some other backends to this that exist. And unfortunately, we're just right about on time. So I'll just quickly mention some of the other big data packages that exist as well. Especially when it comes to bioconductor. So a challenge with R is always that R expects data to be loaded into memory. And so if you have data that doesn't fit into memory, it's going to be a challenge to work with it. So you need to have some kind of package that can utilize a file-based backend, so you don't need to load all of the data at once. There's a few different packages that exist for this on Bioconductor. There's also some on CRAN, but I'm going to focus on the Bioconductor ones. So there's a package called Delayed Array that provides kind of a front end that multiple backends can be plugged into. So Delayed Array just provides a front end of delaying operations to avoid unnecessary computation. So for example, if you want to standardize every column of a huge data set, Delayed Array can do that without actually modifying all the original data. Instead, once you access a column, it'll be standardized once you access the data. HDF5 array is built on top of Delayed Array, and it uses an HDF5 format, which is a scientific file format, as the backend. So this is one of the more mature R packages for working with big data on Bioconductor. And then there's another package called Matter, which is one of the packages that I've developed for use with Cardinal. And so this provides a more flexible approach that might be a little bit more difficult to use out of the box than something like HDF5 array, but provides a lot of allows the user to specify from a lot of different custom storage formats. It doesn't use any particular file format, but it allows you to specify kind of exactly where the data is stored if you want. And I designed this package specifically with kind of the needs of mass spectrometry data, specifically mass spectrometry imaging data in mind. So it's designed to kind of handle some of the requirements of a file format like INZML. So some just quick tips for using any of these packages. You want to avoid accessing the entire data set because it's going to R will try to load it all into memory at once, which is not going to work. So instead, the way that you would approach working with these kinds of data sets is to work on small chunks of the data. So you chunk by rows, chunk by columns, but we are operating on small parts of the data set at once, and ideally utilize parallel computing wherever you can. And again, I'm sorry that we ran out of time. I think that's we're just running out of time right now, but there is examples of some use of some of these packages in the associated R Markdown document that you all have access to. So I'll go ahead and end it here. And since our time is up, and I'm happy to try to answer any additional questions that you have if anyone wants to stick around and wants to know more about something in more detail. And thank you, everyone, for attending, and I hope everyone enjoys the rest of the sessions this week. Thank you, everyone. I do wish we had more time, and if we were in person, this would have been kind of a whole day, but I try to cover as much content as I kind of can. I realize that means a bit of a more shallow coverage of some of these topics, but I hope the R Markdown documents can be useful. All right, well, I'm not seeing any questions, so we'll go ahead and wrap it up. All right, thank you again, everyone, for joining for this intermediate R crash course session. Thank you for all the questions that you asked. I again hope that the R Markdown document is useful and you have access to the example package as well. So feel free to take a look at those, run all the examples on your own time, and And you can hopefully next year or in the coming years, we'll be back in person and we can go through some of these things in more detail again. But for now, I'll go ahead and say goodbye. Have a great afternoon and enjoy the rest of your